Hello, everyone. So, this is going to be our first lesson in probability. Today, we have notes on probability distributions, specifically initial probability. Just a heads up, this is in our Canvas course, and this is our notes right here. It's a PowerPoint. I have them printed out, so I'm going to go based off the printout. Note 6.1, probability distributions. So let's start with just thinking. What is the probability of rolling an odd number on a six-sided die? Well, if I'm rolling a six-sided die, I could get a 1, a 2, a 3, a 4, a 5, or a 6. Now, which of these are odd numbers? 1 is odd, 3 is odd, and 5 is odd. So 3 out of a total of 6 is the probability. 3 out of 6, which reduces to 1/2. So what is the probability of rolling an odd number on a six-sided die? It's about 1 in 2. Or I have like a 50% chance of rolling an odd number. What is the probability of picking out a face card, king, queen, or jack in a standard deck of cards? So I know a lot of us might not know about a standard deck of cards, but there's 52 cards in a standard deck with 4 different suits. That means I have an ace, a 1, or ace is 1, sorry, a 2, a 3, a 4, 5, 6, 7, 8, 9, 10, jack, queen, and king, and I have 4 of these. I have 4 suits, meaning I have 4 jacks, 4 queens, and 4 kings. So if I'm trying to pick out a face card, the possible that I could pick out is 4, 8, 12 out of the total, or 52 cards. We reduce this. We're going to divide both of these by 4 and get 3 out of 13. So I have a 3 in 13 chance, 1, 2, 3 out of 13 chance of getting a face card out of a standard deck of cards. So again, we list the possibles and we divide it by the total. Possibles divided by total. That's what we're looking at when we're looking at probability. So we have a little bit of notes that we want to take with this, and that's what's below. So we have random processes. There's no individual outcome is predictable. So if I'm flipping a heads or tails, I don't know what it's going to be. So just a heads up, that's on random processes. And that's where we flip a coin. So let's go ahead and flip this coin and see, and then we'll come back to random processes. So imagine you're flipping a fair coin, one that is equally likely to land heads or tails. Without flipping a coin, record a random arrangement of heads and tails as though you were flipping a coin 10 times. Label this hypothetical result. So here's our hypothetical result. So let's say I flip a coin. I think the first one's going to be heads. Then I flip again. I think it's going to be tails. Then I flip again. Maybe it'll be a tails again. Then I flip again. Maybe a heads. Flip again, tails. Flip again, possibly a heads. Flip again, maybe a heads. Flip again, maybe a heads. Flip again, tails. Flip again, tails. Now let's see what we would really get if we do this. So if I go to coin flip, I can see. So on the first flip, I get a tails, and I'm recording this. And on my second one, I get a heads. This is my real result. On my next one, I get a heads. Next one, I get a heads. Next one, I get a heads. Next one, tails. We have 4 more. This is my 7th flip. I got a heads. My 8th flip. I got a heads. My 9th flip. I got a tails. And my 10th and last flip, I got a tails. So let's now, so we've done our real result. Let's see what happens. How is this hypothetical result different from the real result? Well, most of mine didn't match up to what I actually got. We need to make at least 2 observations. Most single rounds were incorrect. Also, in the hypothetical result, I thought I was going to get 1, 2, 3, 4, 5 heads. In hypothetical, I thought I would get 5 heads, which is about half. And in the real result, I got 1, 2, 3, 4, 5, 6 heads. So in the real result, I got 6, but in the hypothetical, I got 5. Is the real result experimental data? Did we do an experiment, or is it theoretical, what we think will happen? The real result is experimental data. We did an experiment. We actually did something. The hypothetical result is theoretical data. Or if I were to do a simulation, that would be a theoretical data. But we did something. We flipped a coin. Even if it was on Google, we still flipped a coin. Okay. Like I said, these are random processes. We did not know if I was going to get a heads or tails any one time. We can't tell that. It's random. So no individual outcome is predictable. These are going to include rolling a die. When I roll a die, I don't know if I'm going to get a 1, 2, 3, 4, 5, or 6. Flipping a coin, drawing a card, spinning a game board piece. All of these have an equal chance of happening. Now we have experimental versus theoretical probability. Experimental probabilities are based on trials and observations. So like when we actually flip the coin, and I could have a coin here, I really rolled a die. It can happen through trials or simulations, and the simulations represent the random processes electronically. So like we did, it's not what we think is going to happen, it's what really happened. Simulations help you to explore the different outcomes or results. Theoretical probability can be done without doing an experiment. You create the ratio of desired to possible. So what do I want over all the total possible outcomes? So if I want to roll a 2, that's 1 desired outcome.
Please dial extension 100. Mr. Williams, dial 100.
Like you're really in class. If I rolled if I want to get a 2 out of all the possible die rolls, there's 1 desired outcome out of 6, or 1 in 6 chance. So theoretical probability, we're doing math. Experimental probability, we're actually doing it and seeing what happens. Events. An event consists of 1 or more outcomes. So I flip a coin twice. That's an event. A simple event consists of only 1 outcome. If an event is not simple, it is compound. So a simple event is like I flip a coin. A compound event would be I flip a coin and roll a die. Or I flip a coin and take out a card from the deck. I flip a coin and then I flip another coin. Those are compound events. Finding probabilities. You could list all possible outcomes, but this can get tedious and waste time. We could also do graphs. What is the theoretical probability of rolling a sum of 6 with a pair of dice? So I could do a graph to figure that out. And what would that graph look like? And I'm trying to get a piece of paper ready for us to see what that graph looks like. So if I wanted to know what is the probability of rolling a sum of 6 with a pair of dice. So I would do, I have a pair of dice. So the first dice I could get a 1 through 6. On the second dice I could get a 1 through 6. Where do I have a sum of 6? 1 and 5 make a sum of 6. 2 and 4. 3 and 3, 4 and 2, 5 and 1. So I have a 5 out of total 6 times 6, 36 chance of rolling a sum of 6. 5 in 36 chance of rolling a sum of 6. Now, again, this is a theoretical probability because I didn't actually roll anything. I didn't simulate it. I didn't do anything. This is just what I theorize would happen. This would be a graph to determine how to do that. Again, I got 5 because 1 plus 5 is 6, 2 plus 4 is 6, 3 plus 3 is 6, 4 plus 2 is 6, 5 plus 1 is 6. This is my first dice, my second dice. That's a 5 out of 36. I know it's 36 because there's 6 chances over here, 6 chances over here. 6 times 6 is 36. That'll give me the total number of chances. And you could really go in and count all of these possibilities, but you can just multiply too. So that's how you would use a graph. Sometimes I like just listing out the possibilities. And lastly, what is the probability that any two real numbers you select at random between 0 and 6 have a sum that is less than or equal to 5? So let's do the same thing. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So it's between 0 and 6. Sorry. Need to add 0 up here on both of these. So, and these can go 0 to 6 this way too. There's nothing wrong with how you number them as long as you number them in order. That is less than or equal to 5. So 0 plus 6 is not less than or equal to 5. 0 plus 5 is, and so is anything less than that. 1 plus 6 is not, 1 plus 5 is not, that's 6, but 1 plus 4 is. And anything less than that. 2 plus 6 isn't, 2 plus 5 isn't, 2 plus 4 isn't, but 2 plus 3 is. And as you can see, we eventually get a line. This is like a, if you think of inequalities, linear inequalities, this is going to be very similar to that. And then again, we can count up all the possibilities. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. The 21. Out of this time, there are 7 possibilities over here. 0 through 6 is 7. And 7 possibilities over here. So 21 out of 7 times 7 is 49. We reduce that to 3 7s. I have a 3 in 7 chance of randomly selecting 2 numbers that have a sum between 0 or that a sum that is less than or equal to 5, and these 2 numbers can be between 0 and 6. So that's another way a graph can help you. So let's practice some more. Hannah has observed that her coach does not coordinate the color of his socks to anything else that he wears. Guessing that the color is a random selection, she records these data during 3 weeks of observation. Black, white, black, white, black, white, black, red, white, 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 black, black. Ooh. What is the probability that he will wear black socks the next day? So we need the probability of black, and this is how you write that. P means probability of, and we're going to put black in parentheses. Now, there are 1, 2, 3, 4, 5, 6 times that he wore black in the last, and we got to count all the times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So it was 3 weeks, 15 days, because 5 days for the work week. This reduces to 2/5. So you have a 2 in 5 chance of choosing black socks. Now, again, as a reminder, it's the what we want value over the total value. Again, what we want over total. If we come back to it, desired to possible. The desired amount is the number of black over all of the total amounts, or the possible amounts, 15. So what about white socks? So the probability of white, and I recommend you pause this, try this yourself. Don't always wait for me to give you the answer. Is 1, 2, 3, 4, 5, 6, 7. It's 7 out of our total of 15, which just stays 7 over 15. It doesn't reduce. And then what about Red Sox? So the probability of red, we have 1, 2. So 2 out of 15. Again, this isn't going to reduce. And does that encompass all of our possibilities? Black, white, and red were the only possibilities. 6 plus 7 is 13, plus 2 is 15. That is everything accounted for, 15 out of 15. Now, are the probabilities you found in 1A experimental or theoretical? Now, since this is based on actual data that she recorded, this is experimental data. She actually recorded this, Hannah did. So this is going to be experimental data. Now, if it's just based off the socks he has on his drawer and we're thinking about possible what he would wear, it's theoretical. But since this is actual data, it's experimental. Let's look at another. This table shows numbers of students in several categories at Ridgeway High. And I know it's a little bit hard to see, so I'm going to zoom in a little bit. Find the probabilities described below. Express each answer as a percentage to the nearest whole percent. So first of all, we got to get some totals in here. And I'm going to use Desmos to help us out with those totals. So let's get in here. Okay, so males are 263 plus 235 plus 228. That's a total of 726. So what I did was just total the 10th grade males plus 11th grade males plus 12th grade males. So this number is males in 10th grade. 235 is males in 11th grade. 228 is males in 12th grade. 249 is females in 10th grade. 242 females in 11th grade. 207 females in 12th grade. To get all the females, I'm going to add all of these up together. So 249 plus 242 plus 207, and I get 698. Now, likewise, we need to add up across to get the total amount of 10th graders. So 263 plus 249 is 512. I'm going to double check that in Desmos just because sometimes you want to double check yourself. 263 plus 249 is 512. 235 plus 242 will give us the total 11th graders, and that's going to be 477. And then the total 12th graders is 228 plus 207, which is 435. Now, to get this total in the corner, you're either going to total the column or the row. No matter what, it's going to be the same answer. So let's make sure that happens. 726 total males plus the total females, 698, is 1424. Let's make sure. Total 10th graders is 512. Total 11th graders is 477, and total 12th graders is 435, which is also 1424. So we did get that correct. Okay. Now we can start doing those probabilities. What is the probability that a randomly chosen student is female? Well, the total number of females is 698. So 698 is the desired. We want females out of all possible people is 1,424. Now, I could reduce this. I'm not going to ask. You don't have to reduce, but you can reduce this at this point. What is the probability that a randomly chosen student is an 11th grader? So out of all students, so again, out of 1,424, how many are 11th graders? 477. What is the probability that a randomly chosen 12th grader, so this is out of 12th graders, and there are 435 12th graders, what's the probability that a 12th grader is male? Male 12th graders are 228. So it's 228 out of 435. This time that total has changed because it's out of 12th graders, how many are male? There are 228 males out of 435 12th graders. What is the probability that a randomly chosen male, so out of all males, 726, that it's a 10th grader? There are 263 10th graders out of 726 total males. So that's how you would use one of these charts to fill out probabilities. Next up, Find each probability. Each day, your teacher randomly calls on 5 students in your class of 30. What is the probability that you will be called on today? Write this as a ratio. So you have a 5 out of 30 chance on being called today. If we were to reduce this, it's a 1 in 6. Ratios can also be written as 1:6, like that. So you have a 1 in 6 chance of being called on. 5 out of 30 reduces to 1 in 6. If 2.5% of the items produced by a particular machine are defective, then what is the probability that a randomly selected item will not be defective? Write this as a ratio. Well, if 2.5% are defective, that means 97.5% are not defective. Now, 97.5 is out of 100 because percent is always out of 100. Now, we don't necessarily like decimals, so I'm going to multiply both of these by 10 and get 975 out of 1,000. We could reduce this at this point. I'm okay if you leave it like this. But you have a 975 in 1,000 chance of not being defective. Meaning only 25 out of 1,000 are defective. What is the probability that the sum of 2 tossed dice will not be 6? Write this as a percent. Well, earlier we figured out that the sum of 2 tossed dice that would be 6 is 5 out of 36. So sum is 6 was 5 out of 36. So the not would be 1 minus 5 out of 36. Or 36 out of 36 minus 5 out of 36, giving us 31 out of 36. So when you want to know not something, you can take something that you know is true, like there's a 5 in 36 chance of having a sum that is 6, but not would be 1 minus that possibility, because there's 31 other chances where you're not a sum of 6. And you can either have a sum of 6 or not have a sum of 6. There's no other thing that you could be. So that total would have to equal 1. 5 plus 31 is 36. Out of 36 is 1. All right, couple more and we're done. Find the number of equally likely outcomes of each event described for a roll of 2 dice. Then write the probability of each event. So we have 2 dice, and we want to know what's the probability that it's going to sum to 9. I'm going to do this 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I want a sum of 9. 3 plus 6 is 9. 4 plus 5 is 9. 5 plus 4 is 9. 6 plus 3. That's a 4 in 36 chance or a 1 in 9 chance. Oh, funny, it's a 1 in 9. That doesn't always happen. The dice sum to 6. We already know that's a 5 in 36 chance. But I can do that in a different color so we can see that even on this chart. So a sum of 6 would be 2 and 4. This is a different color. 3 and 3, 4 and 2, 5 and 1. We forgot 1 and 5. So that's a 5 in 36 chance. The dice have a difference of 1. And it doesn't say which one has to go first or not. We're going to do another chart. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So let's subtract them. 1 minus 1 is 0. 2 minus 1 is 1. 3 minus 1. Nope, none of the rest of these are going to work. But 3 minus 2 works. 4 minus 3 works. 5 minus 4 works. 6 minus 5 works. So does this 6 minus this 5. Oops. So does this 5 minus this 4. 4 minus 3. 3 minus 2. 2 minus 1. So if we put all of this together and disregard this in the center, I apologize for that. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 Again, we have a total of 36 options, which is 5 out of 18 when you reduce. Because 2 minus 1 is it, so is this 2 minus 1. Doesn't say which one has to go first, just said a difference. So we have a 5 in 18 chance of a difference of 1. The sum of the dice is 6, and their difference is 2. Okay. Well, the dice sum to give us 6 on this line right here. 5 plus 1, 4 plus 2, 3 plus 3, 4 plus 2, 5 plus 1. Now, which of these would also give us a difference of 2? Well, 4 and 2 would. So it would be this one, because 4 minus 2 is 2. 4 plus 2 is 6. It would also be this one, because it also has a 4 and a 2. 4 minus 2 is 2. 4 plus 2 is 6. So we have a 2 out of the total 36. 2, if I roll, I have a 2 in 36, or a 1 in 18 chance of the dice summing to 6 and their difference being 2. And then the sum of the dice is at most 5. We have done this already. We said that was this one right here, where we have at most 5. You can be 5, you can be less than 5, but at most you can be 5. And that was but this is dice this time, so we do have to be a little bit careful. It's not just adding numbers, it's dice. So let's do another chart so we can make sure we do this correctly. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So the sum is at most 5. So it can be 5, but it can be at most 5. 4 plus 1 is 5, and so is everything less than that. 2 plus 3 is 5, and everything less. 3 plus 2, 4 plus 1. We have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out of 36, which is 5 out of 18. A 5 in 18 chance. The graphs are really helpful here. The probability for classes' number of siblings is represented in the table below. Complete the table. So probability always has to add up to one whole or one total amount. So first let's fill this out, because you can either have 0 siblings, 1 sibling, 2 siblings, 3 siblings, or 4 or more. You can't have any other possibility. There's no negative siblings, and this encompasses 4 or more. So right now we have 0.1 plus 0.24 plus 0.39 plus 0.04. Let's throw that in Desmos. And that gives us 0.77. But we need to have one whole. So this missing spot right here is 1 minus 0.77, because this needs to be 1 altogether. All those percentages have to add up to 1. This is telling us 10% of people have 0 siblings, 24% 1, 39% 2, 4% 4 or more. What about 3? How many people have 3 siblings? That would be 0.23 or 23%. So that's how you would fill out the table. What is the probability of having at least 2 siblings? So you have 2 siblings, 3 siblings, or 4 siblings. It's at least 2. So that's 0.39, possibility of 2, plus the possibility of 3, plus the possibility of 4 or more. You add up all of those. Now this is when you're starting to add different events. So not only can I have 2, I could have 3, I could have 4. So 0.39 plus 0.23 plus 0.04 is a 0.66 or 66% chance of having 2 or more siblings. Find the probability that x is less than or equal to 1. What does it mean? So the probability, it means the probability of having 1 or less siblings, which is the probability of 0 or 1. 0.1 plus 0.24 is 0.34. Now, if we had to do this out of in a ratio, we would do 34 out of 100. 34 out of 100. And I got 0.34 by doing 0.1 plus 0.24 because x is less than or equal to 1. So it could be 1 or less than 1, which is 0. If you go to Canvas, again, there's your assignment. If we go to Canvas, that was your notes. Your assignment is up here. Go ahead and complete it in Google Docs or Kami or on a separate sheet of paper and make sure to upload your work. There's not a ton of questions. There's 4 questions, but it is going through everything that we did. Looking at question 4, I can see that we didn't expressly go over one like that one. 35% would be 0.35. 50% would be 0.5. So if you ever need to change a percentage to a decimal, you either move the decimal to the left twice or divide by 100. Either way works. That is all I have for you today. If you have any other questions, please email me. Have a wonderful day.